welcome to this problem walkthrough. Today, we'll be exploring LeetCode problem number 1041, robot bounded in circle. In this problem, we analyze a robot's movement pattern to determine if it remains bounded within a circle. Let's dive in and unravel the solution step by step. In this problem, we have a robot that starts at the origin, which is the point 0, 0, on a 2D plane. Initially, the robot is facing north, aligned with the positive y-axis. The robot can follow one of three possible instructions, G, L, or R. If the robot receives G, it moves one step forward in the direction it is currently facing. If it receives L, it turns 90 degrees to the left, which is counterclockwise. Similarly, if it receives R, it turns 90 degrees to the right, or clockwise. The sequence of instructions given to the robot is executed repeatedly forever. The task is to determine whether the robot's movement is bounded, meaning it never leaves a circular region on the plane. If the robot is bounded in a circle, we return true, otherwise, we return false. The input to our problem is a string consisting of the characters G, L, and R, and the output is a Boolean value indicating whether the robot is bounded or not. Consider the first example where the input is GGLLGG. The robot starts at 0, 0, facing north. First, it moves forward twice, going from 0, 0 to 0, 1, and then to 0, 2, still facing north. Then, it turns left twice, which makes it face south. Next, it moves forward two more steps, returning from 0, 2 to 0, 1, and then back to 0, 0. At this point, the robot is at its starting position but is now facing south. Since the robot ends up back where it started after completing one sequence of instructions, and the sequence repeats forever, the robot remains bounded in a circle. Therefore, the output is true. Now let's look at the second example with the input GG. Here, the robot starts at 0, 0, facing north. It moves forward twice, first going to 0, 1, and then to 0, 2. Since there are no turning instructions, the robot continues moving straight north indefinitely with each repeated sequence. This means the robot does not remain within a bounded region, instead, it keeps moving farther away from its starting point. As a result, the output is false, because the robot is not contained within a circle. Finally, in the third example, the input is GL. The robot starts at 0, 0, facing north. First, it moves forward one step to 0, 1, still facing north. Then, it turns left, which makes it face west. When the sequence is repeated, the robot traces a square path, moving forward, turning left, and repeating the process. Over time, this square path ensures that the robot remains bounded within a circular region. Therefore, the output is true. Additionally, note that the problem includes constraints, such as an input length between 1 and 10,000, and characters limited to G, L, and R. Some edge cases to consider include inputs with only G, where the robot moves endlessly in a straight line, or inputs with only L or R, where the robot continuously rotates in place. These scenarios can help us determine whether the robot remains bounded or not in various situations. To solve this problem, we need to determine whether a robot following a sequence of instructions is bounded within a circle. The idea of being bounded means that the robot either returns to its starting point or is confined to a repeating motion that prevents it from moving infinitely far away. One approach we can consider is a brute force simulation. The intuition here is simple: if the robot's movement is truly bounded, repeating its instructions multiple times, such as 4 repetitions, since direction cycle every 4 rotations, should reveal whether it eventually comes back to its origin or enters a repetitive loop. To implement this, we first parse the instruction string, then simulate the robot's movements step by step, tracking its coordinates and direction for up to 4 cycles. Finally, we check if these movements bring the robot back to the origin or indicate a repetitive pattern. The computational complexity of this approach is n*k, where n is the length of the instructions and k is the number of repetitions, which in this case is a constant value of 4. Additionally, the space complexity is O(1), as we only track the robot's position and direction throughout the simulation. This brute force approach, while intuitive, has some significant drawbacks. It explicitly simulates multiple cycles of instructions, which can be inefficient for large inputs. If we can determine boundedness directly from a single pass through the instructions, then repeating the same cycles becomes unnecessary. This leads us to an optimized approach that leverages geometric reasoning. The key insight here is that the robot's behavior after one complete cycle of instructions determines whether it is bounded. Specifically, if the robot returns to the origin at the end of one cycle, it is clearly bounded. Alternatively, if it doesn't return to the origin but its direction has changed, it will eventually loop back to the origin after multiple repetitions. However, if the robot neither returns to the origin nor changes direction, it will continue moving infinitely away, which means it is unbounded. To implement this, we initialize the robot's position and direction, then process the instruction string in a single pass. For each instruction, we update the robot's position when it moves forward, or adjust its direction when it turns left or right. After processing the instructions, we evaluate the final position and direction to determine whether the robot is bounded. This optimized approach has a significant advantage over the brute force method in terms of efficiency. Since we only process the instruction string once, the time complexity is reduced to O(n), where n is the length of the instruction string. The space complexity remains O(1), as we only need to track the robot's current position and direction. This eliminates the overhead of simulating repeated cycles. The simplicity and efficiency of this approach make it an excellent choice for solving the problem. The key observation that underpins this strategy is that the robot's movement behavior after one cycle is sufficient to determine whether it is bounded. By recognizing that a change in direction ensures a loop, and that returning to the origin confirms boundedness, we avoid redundant calculations. This realization was an aha moment in developing the solution, as it allowed us to focus on the robot's final state after one cycle rather than simulating multiple repetitions. When comparing the two approaches, we see clear trade-offs. The brute force simulation has the advantage of being straightforward and easy to understand, as it simply repeats the instructions and observes the robot's behavior. However, it is inefficient, especially for larger inputs, since it involves redundant computations across multiple cycles. On the other hand, the optimized approach provides a more elegant solution. By analyzing the robot's motion in a single pass, it achieves O(n) time and O(1) space complexity. The drawback is that it requires a deeper understanding of geometric constraints and direction changes, which might not be immediately intuitive. Ultimately, the optimized approach is the better choice because it directly analyzes the robot's motion without unnecessary repetition, making it both faster and more resource efficient for practical use. To solve this problem, we need to determine if a robot, following a sequence of commands, is confined to moving within a circle. The robot starts at the origin, facing north, and it can interpret three types of instructions. The command G moves the robot one step forward in its current direction. The command L turns the robot 90 degrees to the left, and R turns it 90 degrees to the right. For the robot to be considered bounded within a circle, one of two conditions must hold: either the robot returns to its starting position after executing the instructions once, or the robot changes direction in such a way that repeating the instructions indefinitely will eventually form a cycle and keep the robot within a confined area. These are the criteria we'll use to determine boundedness. Now, to represent the robot's movement, we consider the four cardinal directions: north, east, south, and west. We assign each of these directions an index 0 for north, 1 for east, 2 for south, and 3 for west. Using modular arithmetic, we can efficiently calculate direction changes. When the robot turns left with the L command, we decrease the direction index by 1, and when it turns right with the R command, we increase the direction index by 1. Both operations are performed modulo 4 to ensure the indices stay within the range of 0 to 3. This simple representation helps us track the robot's orientation without needing to handle complex angle calculations. To simulate the robot's movement, we start at the origin, with coordinates x equals 0, y equals 0, and initialize the direction index to 0, meaning the robot is facing north. As we iterate through the sequence of instructions, the robot responds to each command accordingly. For G, the robot moves one step forward in its current direction. This means incrementing y for north, incrementing x for east, decrementing y for south, or decrementing x for west. For L and R, the direction index is updated based on modular arithmetic as we discussed earlier. Once all instructions are processed, we check two conditions to determine if the robot is bounded. First, we see if the robot has returned to the origin, as this guarantees boundedness. If not, we evaluate the final direction. If the robot is not facing north, repeating the instructions will eventually create a cycle, making the robot bounded. On the other hand, if the robot ends up facing north and is not at the origin, it will continue moving indefinitely, meaning it is unbounded. The key insight here is that a robot's movement is bounded if repeating the instructions results in a closed trajectory. This happens in one of two scenarios: either the robot returns to its starting point, or it ends up facing a direction other than north after executing the instructions once. By leveraging modular arithmetic, we can efficiently handle direction changes without the need for extra data structures. The robot's position, represented by x, y, and its direction index are sufficient to determine whether it is bounded. The instructions themselves are stored in a simple list, which we loop through only once. To optimize our solution, we avoid simulating more than one repetition of the instructions, as the outcome of boundedness is entirely determined by the robot's position and orientation after the initial execution. Finally, let's analyze the complexity of our approach. The time complexity is O(n), where n is the number of instructions, as each command is processed in constant time. This means the algorithm scales linearly with the size of the input. The space complexity is O(1), because we use only a fixed number of variables to track the robot's position and direction, regardless of the length of the instruction sequence. This makes the algorithm very efficient in both time and space, ensuring it can handle large inputs seamlessly. The provided Python solution tackles the problem of determining whether a robot moves in a bounded circle based on a sequence of instructions, G, L, R. Here's the detailed explanation. 1. Initialization. We define the possible directions the robot can face as 0, 1, north, 1, 0, east, 0, -1, south, and -1, 0, west. These are stored in a list called directions. The robot starts at position 0, 0, origin, and faces north, index 0 in the directions list. 2. Instruction processing. We iterate over each character in the instruction string. If the instruction is go, the robot moves one step forward in its current direction. The direction is determined using the direction_index. The corresponding dx, dy values are added to x, y to update the robot's position. If the instruction is L, left turn, the robot turns 90 degrees counterclockwise. This is achieved by decrementing direction_index by 1 and taking the modulo 4 to ensure it wraps around circularly. If the instruction is R, right turn, the robot turns 90 degrees clockwise. This is done by incrementing direction_index by 1 and taking the modulo 4. 3. Circle check. After processing all instructions, two conditions determine if the robot is bounded in a circle. If the robot returns to its starting position, 0, 0, it is clearly bounded. If the robot does not face north, direction_index equals 0, repeating the instructions will eventually lead it back to its starting position, forming a circular trajectory. The function returns true if either condition is met, indicating the robot is bounded in a circle. Otherwise, it returns false. This solution is efficient with a time complexity of O(n), where n is the length of the instruction string, and a space complexity of O(1), as it uses a fixed amount of additional space. This is the Java implementation of the LeetCode problem number 1041, robot bounded in circle. The logic mirrors the Python implementation, where the robot's movement is tracked using a direction array and coordinates. Key differences include the explicit use of Java syntax for arrays and loops, and the type declarations for variables. The solution determines if the robot is bounded in a circle by checking if it returns to the origin or ends up facing a different direction after processing all instructions. In this example, we start with the robot at position 0, 0, facing north, which corresponds to a direction index of 0. The instructions given to the robot are GGLLGG. Let's break this down step by step. First, the initial state is straightforward. The robot is at position 0, 0, and facing north. Now, the first instruction G means the robot moves one step forward in the direction it is facing, which is north. Movement in the north direction corresponds to a change in the y coordinate by 1, so the new position becomes 0, 1. The next instruction G is another forward move in the same direction, so the y coordinate increases again by 1, resulting in a new position of 0, 2. Now, the robot encounters the instruction L, which means it turns left. Turning left decreases the direction index by 1, and since the values wrap around using modulo 4, the new direction index becomes 3, which corresponds to facing west. Another L instruction follows, causing another left turn. This time, the direction index decreases from 3 to 2, which means the robot is now facing south. The next instruction G tells the robot to move forward in the south direction. Movement in this direction decreases the y coordinate by 1, so the new position becomes 0, 1. Another forward move, another G, continues in the south direction, reducing the y coordinate by 1 again, bringing the robot back to its starting position at 0, 0. Finally, we check the outcome. The robot has returned to its original position, so it is bounded in a circle. The result is true. In the second example, the robot is given the instructions GL. As always, the robot starts at position 0, 0, and faces north. The first instruction G moves the robot one step forward in the north direction, updating the y coordinate to 1. The new position becomes 0, 1. Then, the second instruction L tells the robot to turn left. A left turn decreases the direction index by 1, and modulo 4 calculations give a new direction index of 3, meaning the robot is now facing west. At this point, we perform the final check. The robot does not return to the starting position, but since it is no longer facing north, we know that if the instructions were repeated, the robot would eventually form a circle. Therefore, the output is true. In the third example, the instructions are GRGRGRG. Starting at position 0, 0, and facing north, the robot first encounters G, which moves it one step forward in the north direction. This increases the y coordinate by 1, so the new position is 0, 1. The next instruction R tells the robot to turn right. A right turn increases the direction index by 1, resulting in a new direction index of 1, which corresponds to facing east. The robot then processes another G, moving forward in the east direction. Movement in this direction increases the x coordinate by 1, so the new position becomes 1, 1. Following this, the robot processes another R, turning right again. This increases the direction index from 1 to 2, meaning the robot now faces south. The next instruction G moves the robot one step forward in the south direction, decreasing the y coordinate by 1. The new position becomes 1, 0. Then, another R causes the robot to turn right, updating the direction index to 3, which corresponds to facing west. The final G moves the robot one step forward in the west direction, decreasing the x coordinate by 1. This brings the robot back to the starting position at 0, 0. For the final check, the robot has returned to its original position, completing a loop. Therefore, the output is true. The time complexity of this solution is O, n, where n represents the length of the input string, instructions. This is because the algorithm processes each character in the string exactly once. For each character, it performs a specific operation depending on whether the instruction is G, L, or R. If it's G, the robot's position is updated using simple arithmetic, which takes constant time. If it's L or R, the direction is updated using modular arithmetic, which also takes constant time. After processing all the instructions, the algorithm performs a final check to determine if the robot is back at the origin or not facing north. These checks involve simple comparisons and also take constant time. Adding all these steps together results in an overall time complexity of O, n. The space complexity of this solution is O, 1, which means it uses a fixed amount of memory regardless of the size of the input string. The algorithm maintains a small set of variables, the directions array, which holds 4 tuples representing movement directions, and 3 scalar variables x, y, and direction underscore index. These variables require a constant amount of space that does not grow with the size of the input. Moreover, the algorithm avoids using any additional data structures like lists or hash maps that depend on the input size. This ensures the memory usage remains constant, leading to a space complexity of O, 1. The optimal solution is much more efficient compared to a brute force approach. A naive method might try to simulate the robot's movement over multiple cycles of the instructions, repeatedly checking for patterns like returning to the origin. This would significantly increase the time complexity, potentially reaching n*k, where k is the number of cycles examined. In contrast, the optimal solution processes the instructions just once, focusing on the robot's state after one pass. This ensures a linear time complexity of n. Mathematically, since each instruction is processed exactly once in O1 time, and the condition checks at the end are also O1, the overall runtime is directly proportional to the size of the input, making it n. The space complexity remains constant at O1, as no additional memory is used beyond the fixed variables. In the best-case scenario, the input string is either empty or contains only a single instruction. Here, the algorithm executes in O1 time, as there's minimal work to do. In the worst-case scenario, the input string is very large, requiring the algorithm to process each instruction, resulting in n time. However, the space complexity remains O1 in all cases, as the memory usage does not depend on the input size. The solution achieves this efficiency by leveraging simple arithmetic operations in modular arithmetic, avoiding unnecessary repetition or additional data structures. This makes the algorithm highly efficient, outperforming brute force methods with its linear time complexity of n and constant space complexity of O1. One of the most common mistakes made in this problem is assuming that the robot must return to the origin after one cycle of instructions to be considered bounded. This isn't true because a robot can still be bounded even if it doesn't end up at the starting point, as long as its movement forms a repeating loop or it changes direction in a way that prevents it from escaping its trajectory. For instance, a command like GL doesn't bring the robot back to the origin, but it still results in bounded movement. Another frequent oversight is ignoring the direction the robot faces. While tracking the robot's position is important, its orientation, whether it's facing north, east, south, or west, plays a crucial role. A turn to the left or right directly affects the overall trajectory and determines whether the movement is eventually confined. Lastly, failing to consider multiple cycles of movement is another pitfall. You can't always determine boundedness after a single iteration of the instructions. By analyzing how the instructions behave over repeated cycles, you can identify if the robot's path eventually forms a loop or becomes repetitive, which indicates bounded movement. Now, another common mistake is overlooking edge cases with minimal input. For example, simple commands like G, L, or R might seem trivial, but they are important test cases to ensure your implementation correctly handles single instructions and their implications on bounded movement. These cases can often reveal subtle bugs in logic. Additionally, errors in updating the robot's position or direction are a frequent source of incorrect results. Miscalculating the coordinates, such as the x and y positions, or the turning logic for the robot's orientation, like confusing a left turn with a right turn, can lead to wrong conclusions about whether the robot is bounded. Ensuring that these updates are accurate is essential for solving the problem correctly. This problem often appears in interviews to test your understanding of simulation, loops, and geometric reasoning. A key part of solving it is being able to clearly explain how you track the robot's movement and orientation throughout the instructions. The good news is that the problem can be solved efficiently in n time complexity, where n is the length of the instruction string, because you only need one pass to determine the robot's behavior. Another important takeaway is recognizing patterns. Many interview problems require detecting cycles or repetitive behavior, much like in linked list cycle detection. This is an excellent opportunity to discuss general strategies for identifying loops. Finally, communication is critical. Be ready to explain precisely why the robot is bounded, especially in cases where it doesn't return to the origin but instead forms a loop. Related problems, such as LeetCode 141 on linked list cycles or LeetCode 457, which involves detecting cycles in an array, can provide additional context and reinforce these concepts. Another related problem worth exploring is LeetCode 874, which focuses on walking robot simulation. Like this problem, it involves interpreting commands and simulating movement, but it introduces additional considerations, such as obstacles. LeetCode 62, while different, involves reasoning about movement on a grid and can help build intuition for solving grid-based problems. When it comes to alternative approaches, the simulation method is the most straightforward. Here, you simulate the robot's movement step by step, updating its position and direction as you process each command. While intuitive, this approach requires careful attention to detail to avoid implementation bugs. Another option is mathematical analysis, where you analyze the net movement and direction after one cycle of instructions. If the overall displacement is 0 or the direction changes, the robot is bounded. This approach is more abstract but often faster to implement once you fully understand the concept. Both methods have their trade-offs, so choosing the right one depends on your comfort level and the specific constraints of the problem. Great job making it through the solution. We summarized the key points about simulating the robot's movements and determining if it's bounded. Remember, these types of problems test your ability to visualize and simulate scenarios. If you enjoyed this solution, don't forget to like and subscribe, and we'll see you in the next problem. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!